All right. Hi, everybody. This is worksheet 2 on electric flux and electric potential. I'm trying out the iPad setup again, so hopefully we like that. And if we do, we'll just kind of proceed using this modality. I just want to dive into this worksheet because there's 5 problems, a little longer than normal, and there's a lot of explaining that needs to be had. So this is first talk about electric flux, and this is related to Gauss's law. And, we've kind of talked about that before. We had a lecture about it. And the thing to remember here is, yes, it's very challenging in its scope, but within the class itself, we try to limit the questions. In fact, it's something that's normally not even addressed in the class. So because of that, you can kind of expect its relevance to kind of dip off after this point. It also doesn't come back in like in future concepts, like much of everything else does. Okay, so let's first define electric flux. So that's a quantity proportional to the number of electric field lines penetrating any surface of interest that we define as a Gaussian surface. And you should remember that the E vectors, so the electric field vectors, are normal relative to the surface. So what's a normal vector? That's just anything that's perpendicular to, it's like a sphere sometimes, a cylinder, a flat sheet. It's just pointing straight out, right? And you kind of imagine there's like infinitely many of those because it's like a curved surface. So yeah, this is the equation for that. It just basically says, the electric field lines, a quantity proportional to electric field lines is proportional to the surface itself with respect to the number of electric field lines. Sorry. And then let's move to Gauss's law. And this is the electric flux through any closed surface is proportional to the electric charge enclosed in that surface. So you'll kind of see these questions one of two ways. You'll have like one of the 3 common shapes, the sphere, cylinder, or like flat sheet rectangle kind of thing, and there's a charge in it or outside it. And you'll basically be asked to compare the equation in either of those cases. So essentially, with this equation, we can see that the electric flux, which is, this guy right here, is proportional to the total electric charge enclosed. And that represents the total electric charge enclosed. And this is just a constant value. And then that constant value kind of will fluctuate, not fluctuate, I should say. The area is embedded in that. So sometimes you'll have to manipulate as needed. Okay. Again, so Gauss's law is the net electric flux through any closed Gaussian surface. And it's equal to the net charge that's in that surface divided by that E naught right there. Okay. Now let's talk about potential energy. So I have the worksheet here so I can look at you guys too. So the potential energy is the change in PE, and it's directly related to the change in voltage. So they're almost like the same thing. When you're asked for what's the potential at a certain point, you're basically asking for that voltage there. So you have to remember that all these charges, the old charges will spontaneously go from lower potential energies. Will go towards lower potential energies if they're allowed to move. And they'll only move when there's a potential difference, right? And that makes sense. So when you're holding a rock above the surface, it'll want to go to lower potential energy, which is on the floor. So when you drop it, it'll go towards the floor. That same kind of thing applies with these charges here. And also you have to remember that it will only move when there is a difference in potential. So as we'll soon see, or maybe we even discussed it now, when we have something defined as steady state, or they'll say the system's been operating for a long time, we assume that the charge is kind of evenly distributed throughout the system and it's kind of at an equilibrium. In that case, there is no difference in potential, so there won't be any movement in charge. But I'll call that out when we see it. Kind of talked about this. So the electric potential is the amount of work needed to use a unit charge from a reference point to a specific point against the electric field. And we have to remember that electric potential is a negative. So is a scalar. So you plug in the negative when appropriate. Okay. And this is a special situation that we can use to break down this potential energy, this VED. So this exists when there are 2 parallel plates. So that'll be, something that looks like you've seen them before. It's something like this, and there's that field between them, right? So that's a special case that we can use this equation to substitute for V when we're solving potential energy equations. And we'll see an example of that. The important thing to note about this equation is V is the voltage between 2 positions, and D is the distance of separation that will happen. And again, we'll see that. And lastly, there's electrical work. So this is the work needed to move one point to another. So that's very obviously related to the electric potential. And keep in mind that work, energy, and voltage are scalars. So you plug in the negative where appropriate. So if it gives you the number in the question as a negative, you have to plug that in. And that's in contrast to, forces and fields, where you let the vector in the free body diagram agree or disagree to give you the plus or minus. And with this equation here, we're really concerned with the amount of work done by the electric field. Okay, and I left this area over here blank, and I just want to talk about some key things here. I wrote it down so I don't get it wrong. So let me just get it here. So we've now talked about electric force, electric field, and electric potential. So the first one, let's talk about electric force. Okay, so electric force will push a charge directly, right? It's going to be, it's kind of the easiest one to visualize. It's going to be some difference in charge. It's either going to be attracted or repelled. Electric field is an arbitrary label relative to a point like infinite space, which determines the force an electric charge would experience if it was put in that position. So let's say this, electric field. I'll zoom back out. Sorry, I need to zoom in when I write because I have a hard time writing on the iPad. Sorry, I messed up here. Okay, so a point in space which determines the force a charge would experience if it were put at said point. All right, and the last one is electric potential. And again, this is an arbitrary label relative to a point in space, which determines how much energy is required to move a particle from A to B. So I'll write that again. I'll try to be more efficient this time. Sorry. Okay. All right. Sorry, that took a second there, but that's just something you can pause and take a screenshot and write down there. And I want to acknowledge the similarities between gravitational potential energy and electric potential energy, because they both have field forces, right? Gravitational, the potential energy is the result of an interaction between two masses, whereas with electric potential energy, it's the result of an interaction between charges. And we're depending on the charge, the field, the strength, and relative position, that value can fluctuate. Okay. So let's move on to this first one. So this was actually the example we discussed on the homework. And I thought that in addition to the two examples he gave us, this was kind of the only other way it could be asked. So I wanted to address this. Again, I'm going to clarify with him to what capacity he wants you guys to know Gauss's law, because we do need to ramp it up. I definitely want to make sure we cover that on the midterm review here. Okay, so in class, we worried about the cases where there's a charge inside the Gaussian surface. Here we have a charge located Here we have a charge located, sorry, there's a message in the chat. We have a charge located right above the surface, right? So by nature of this question, there is no charge enclosed within the Gaussian surface. Therefore, the total flux is equal to 0. So we're going to say E total is equal to 0. We also know that this value itself is equal to the flux through the flat plus the flux through the curved surface, right? So how we want to visualize this normal vector produced by this charge is it enters in through the flat surface and it works its way through and it comes out the bottom of the curved surface. So because of this, we already know how we're going to define this equation. First, in part A, we're going to find out that E curve is equal to what? Q over E naught. We're dealing with half a sphere, so we're going to multiply by 1/2. That's kind of, it's half the area. And because the normal vector is exiting the Gaussian surface, see how right here, we're exiting. It shoots all the way through, and it's now exiting. It's a positive. It's always a positive. Now there, we have enough to address what it is through the flat surface. Same reason why the 2's there. It's half of the thing. And here through the flat surface, we actually have it entering. When the normal vectors are entering through the flat surface, it's negative. When it's exiting, it's positive. And we'll see that when we combine this theory and this equation, that it'll end up canceling each other out and it'll equal 0. So that's kind of the proof here. What I really want to stress on is the point of this question is the positive with respect to A is because the normal vector is escaping the Gaussian surface. Escaping the Gaussian surface, it's positive. Because in B, we are now entering, remember this curve is right above it. It's entering the Gaussian surface, it's negative. So you set it up. It's just kind of like by definition, this is how it is, okay? And the only other thing is, because the charge is not enclosed in the sphere, the total flux is equal to 0. The 2 other examples, 1 and 2 of week 2's materials related to Gauss's law, relate to the other way this will be asked. And I invite you to watch his recording on that because it's good. All right. So I think that for the time being, let's leave Gauss's law at that. I don't want to, I was talking about it in the beginning with a student, it can get very confusing very, very quick. So let's keep it, in control here. So here we have 3-point charge arranged at the corners of a square of sides L shown. What is the potential at that point A? So I'm going to pause the recording actually when I draw, or I don't even know how to pause anymore because I'm on my, all right. Just kidding. All right, so we have this one here. This is point A. Okay, so what we're asked is what's the potential? When we're asked for a potential, what are we solving for? We're solving for that V value, right? We know V at position A is equal to the role of the other charges on that position. So I'm going to say V1, or I'll call this, I don't want to do this. So that's V1, I'm sorry, that's Q1, that's Q2, and that's Q3. So that means each of these charges are embedded in their relative voltages and their subscripts, V2 plus V3. I can now start to expand with the equation, K, Q1 over R1, plus K, Q2 over R2, plus K, Q3 over R3. Okay, so we can define this as R3. We can define this as R2. And then between this guy, it's root 2. Oh, you can just find that through Pythag, or if you have a good eye, you could just pull that out right away. The next thing I want to do is factor out that K, leaving behind Q1 over R1. At this point, I'm going to plug in the charges as appropriate. So Q1 is just Q. It's okay. So Q over R1. Q2 is equal to minus 2K. So remember, this is a scalar. We plug in the negative. And then plus 3Q over R3. Factor out the Q. We have 1 over R1, which is equal to L. Oh, actually, I don't want to factor yet. I'll just do it from here. So R1 is equal to root 2L. This guy is L, this guy is L. So then we can factor out K, Q over L, leaving behind 1 over root 2 minus 2 plus 3. All right. And then, you can simplify this as you want to. It's a no number question, so we're basically at the end there. And that's that one. So the key thing I want to bring attention to again is the fact that we're dealing with a scalar. We plug in the negative based on how it's given to us in the problem. All right, let me see if I can pause. Oh, here we go. And we're back. The next one we're going to look at is number 3. So this one is applying that work equation. So we have to remember with this work equation, we're really focusing on the work done by an electric field. And remember, that's W equals minus Q delta V. And how do we define a delta in a variable? It's the final minus the initial. One second. Okay. It's related to the final minus the initial. Or, as we'll say here, is that potential from this position to this one. So that means the minus 45V is the final. I'm going to call that VA. Or sorry. VB minus VA. All right. So minus Q, that final position, minus 45. Again, we plug in the negative. And then minus 125. Okay. We should know what the charge of an electron is. You'll plug everything in, and you'll come out with 2.72 times 10 to the minus 17 joules. That's your answer. It should make sense that it's positive because it's like moving through this system here to a negative. Right, so that's just application of the equation where delta V tells us it is the final minus initial, and you always plug in the negative. Let's move it on. All right, so now here's kind of where we become a little bit more tricky and apply what we've been learning. We're asked, what is the change of potential when a minus 2 microcoulomb charge, that used to be right here, is moved from point A to point B, which are 16 centimeters apart. 16 centimeters right there. What is the change of potential energy if the charge is then moved from B to infinitely far away? So let's first deal with that first part of the question. And let's define what we're going to need to solve. What we're looking for is a change in potential energy. This change in potential energy, or delta PE, right? The final and the initial, we're comparing those things, is equal to K delta V. And if we further expand this, we'll see it's Q is VA minus VB. Okay. We now can ask, like, what are we going to need to solve for first? We're going to need VA. We're going to need the potential while it's at A and the potential while it's at B. So how are we going to draw that? We have our little diagram right here. Oh, they already gave us everything in meters. Oh, I can just plug in. Okay. I'll call this part 1, solving for VA. So VA is equal to the effect of, gosh, is that 38? Yeah. That's also 38. 0.24 meters, 0.12 meters. All right, so hopefully that kind of clears that up. So that's the role of these two charges acting on that position. So those two charges themselves are pretty similar. I mean, they are exactly the same. R1 plus Q2, R2. But I'm going to solve them as if they're different, just so we kind of are broader in our scope and we can apply this to the future. Okay, so that's how you would set that up. At this point, you can factor out the K and the Q, leaving behind 1 over R1 plus 1 over R2. And we'll say this is R1 and this is R2. Okay. we can now just plug in everything. The K is a constant, the charge is given, and then our distances are also given. So VA comes out to 4.28 times 10 to the 6 volts, VA. The next thing we need to do is solve for VB. So VB, very similarly, is going to be equal to K, Q1, but now we're going to have a new distance because it's moved up, to over here, plus K, Q2 over R4. So from here to here, let's call this R3 and R4. How do we solve for them? There's going to be some pi bag action here. So R3 is equal to the square root. I'm just going to make it the whole numbers because it's easier to work with. That comes out to be 0.2, and I just then make it, or I guess you can just do this too. Actually, I could do the whole numbers because it's easier to plug in. And then for R4 is equal to 24 squared plus 16 squared. That equals 0.29. We now follow the same principles here. Again, K, Q, 1 over R3 plus 1 over R4. Plug everything in, and what you're going to get is 2.89 times 10 to the 6. So it drops as expected. It's further away at that point. So now we have what VB is. We are now able to solve for what's the potential difference of those point A and those A and B positions with that equation we used before. So we'll say Q delta V is equal to the charge of what we're dealing with here. Oh, it's just they give you the value times 10 to the minus 6, plugging in the negative, minus that final position, 2.89 times 10 to the 6, minus that initial, which is 4.28 times 10 to the 6. All right, what that comes out is 2.78 joules. So that's part one of the question done. Let's call that A. And now in part B, we're asked, what about if it's moved, that particle is moved from B to infinitely far away? Okay, infinitely far away. Right away, this should kind of tell you what to do if you remember from math, that the potential of that position is going to be equal to 0. So why that is the potential at infinity is going to be equal to K Q1 over infinity plus K Q2 over infinity. And any value over infinity is so small, right? The denominator is so big that it's effectively 0. So we call that 0. But that's not what it's asking for. It's asking for the potential difference. So this is where people can get kind of tricked here. Our potential difference is defined as delta PE equals Q, the final position, that's the potential at infinity, minus where it starts from, VB. So this person, I don't know why, I call the variables guy and person sometimes. I don't know why. That's how it works in my brain. But this variable crosses out to equal to 0. And we're left with Q times a minus VB. We're going to clean that all up, and we're going to see that it's equal to 5.78 joules. Okay, and you're going to plug in the negative for Q there, right? Because it's minus 2 microcoulombs. So yeah, plug in the negative in both cases. All right, so I'll do a quick pause here. All right, and let's continue on to our final question. So this was one that I was working on yesterday, and I got really stumped. For the first time in a session, I was like, guys, I can't figure this one out. And I realized that there was a big error in the key, and I caught it, and I made a recording, and I fixed it. But let's just do it right from the first time here. So this is a tricky question, and I would say if this was on an exam, it is exam caliber, but it would be like a hard question on the exam because you have to use kind of a variety of things here to solve it. So we have an electron accelerated from rest by a potential difference of 2,200 volts. It passes through 2 parallel plates that should be ringing the light to use that special equation at some point that are 6.5 centimeters long and 1.2 centimeters apart. The parallel plates have a potential difference of 250 volts. At what angle will the electron be moving after it passes through the plates? So we can imagine here, we have our 2 plates here. Okay. And within these 2 plates, there's field lines, electric field. And that's because we have like pluses on this side, they're parallel plates, minuses on this side. And we have a little particle. So a little particle starts from rest, shoots through, and it hits this field. It's an electron. It starts getting attracted to that plus side, and then it shoots out the other end. Within this whole thing, from here to here, it's I'm just going to convert it to meters, 0.065 meters. Okay, so that means the particle upon exit, I'm going to call that a little minus here, it's going to have a trajectory, whereas an angle theta. I should define it with an angle theta. Okay, so to find theta, we need components. There's a few different ways we can get components. That can be through forces, fields, and then also through velocity. We're going to have an x and y velocity. Initially, it's from rest, so it's 0. But then it gets an x velocity. It starts shooting across along the horizontal plane. It hits this field, and there is a force in the y direction. So we have acceleration in the y direction. So that means we're going to have a velocity in the y direction as it starts shooting up to go this way. Now it has x and y. So the first thing I'm going to ask is for you to recall that potential energy is equal to kinetic energy. So the potential of this system, is Q delta V. We talked about electric potential. And since it's moving, the kinetic energy is 1/2 mv squared, where that V is velocity. We're going to rearrange this equation. We're going to find to isolate velocity on one side. Put a little bar over that. So velocity is going to be equal to the square root of 2q delta V divided by the mass, right? And that delta V, I'm just going to erase here. It's the final minus the initial point. We know it starts at 0 and then it's accelerated, or what did they say? It's accelerated from rest by a potential difference of 2,200. So we can just, the initial is going to be 0. The final is 2,200. So might as well just put it in right there. So now we have an expression for velocity. I'm going to call this velocity in the x direction. You can plug everything in here, and that'll come out to be equal to 2.78 times 10 to the 7 meters per second. Looking at the system, we can see that there's a force. There has to be a force, otherwise the particle would continue in a straight line. That is an electric force pointing straight upwards as it is attracted to that positive side there. Because there's no forces in the x direction, that means there's no acceleration in the x direction. By definition of no acceleration in the x direction, the initial velocity upon entering this parallel plate, so I can call that initial, is equal to the final. There's going to be no change in how fast it's going with respect to the x. Now that brings us, so we have our first component of this vector here, right? So we're going to have our x and y here, and there's going to be some angle theta, right? We got our x, but we need a y. So that moves us to part 2. You can use the equation Vf. So the final velocity with respect to the y is going to be equal to the initial velocity with respect to the y plus the acceleration in the y times time. Okay. And that's equal to the displacement, subtracting of the two velocities, move one to the other side. But I'll just jump ahead to this step because we should recall this equation. What's the initial in the y direction? It's equal to 0. It's only upon entering the field there's an instantaneous attractive force there. So initially there's nothing in the y direction. So now we have an expression where we need to find a y, so acceleration in the y direction, and t. If we recall Newton's second law, we have F, so the sum of forces in the y direction is equal to the mass times the acceleration. Where the force here, say F, is equal to Fe, where Fe is equal to AEQ. Because we're dealing with this parallel plate situation, we're allowed to incorporate, what do I call it? Whatever I call it over here. We're allowed to use this equation. But we're going to have to rearrange it to get E on one side and get the voltage embedded inside. So we're going to rearrange that equation to another one of these guys. We're going to rearrange that equation to E equals V over D. So when we plug everything in here, we'll see that, here we go. It'll be V Q over D, divide both sides by the mass, equals acceleration in the y direction. We now have one thing we can plug in right here. The next thing we need to find is time. So t is going to be equal to the change in position. I'm just going to deal with the x divided by how fast it's going in the x, right? We have to use the x here because we don't know how fast it's going with the y yet, right? It's initially at rest, but we do know that there's a change in displacement as it travels through this parallel plate situation. So that change in x is going to be equal to 0.065. We'll define this as 0, and this is as the end of it, divided by that v naught x from above, and that will be equal to 2.34 times 10 to the minus 9 seconds. We now have something we can plug in for time. Okay. We're now going to do our plugging in of everything, and let's say v final y is going to be equal to vqt over dm. Plug in everything that we have here. We're going to get vfy is equal to 7.9 times 10 to the minus 6 meters per second. All right. We can now go back to that little diagram we drew. We have our vy, we have our vx, and we have this angle theta that's traveling. We just got to do an inverse tan function. So we'll say theta is going to be equal to tan inverse vy over vx. Plug in the velocities we just found, and theta comes out to be equal to 15.9 degrees above the plus x axis. All right, and then the little way of checking your work here is, we're going to define this coordinate system as this. So we're going to expect it to be some positive above the x. So if you come up with a negative there, that should be like, oh, I messed up one of my velocities here. I guess the key thing I want to remind you of is the fact that the potential is equal to the kinetic. Within this special kind of question where we have the two plates, we can use this equation. And that also, don't forget Newton's second law, where all the forces equal to mass times the acceleration. And we need to remember the interconnectedness of these equations, and how we can, from purely this force, find acceleration. Right? Because the force is equal to EQ. We don't know what the field is, but we do know that in this situation where it's constant field between these two plates, we can use E equals V over D, where that's D is that distance. Okay, I'm going to pause that's it for the recording. Finished faster than I anticipated, and I'll take questions.